So on your microcontroller, what constraints did you use to choose that particular one? It ended up being very inexpensive for what you needed. Were there other constraints that you considered?
The question is about why we chose the specific microcontroller and what constraints we considered. We were trying to make the device as small as possible and as cheap as possible. Those were our main constraints. So we ended up using Nano, which is smaller than a piece of gum. It's an inch and a half by half an inch long. So as in the future, we were able to get a smaller solenoid from the inside. All we would have to do is shrink down the pressure housing, and we could make the device even smaller and even easier to deploy and retrieve.
Is that particular microcontroller expandable if you needed to access additional data or track data?
Absolutely. It's because of the company that designs it, it's open source hardware.
Yeah.
So there's a lot of there's an add-on so you can put in a thumb drive so that you have gigs of space to store your data, and there's a lot of possibilities.
That was a great decision.
Yes.
You said that you thought the communication and the GPS portion of it wasn't very important in this particular procedure. When you do actually go to put it into the ocean, how do you keep track of where it is and recovery?
Well, at this point, we would not do an ocean test without a tether attached to it, because if we're going down to 1,000 meters, this thing's going to drip with the currents. So in the original scope of the project, we want the sponsor wanted the entire package, so we want GPS, RF, signals, and it was out of the range of what we were capable of getting done within the 2 semesters, so the scope was changed. But if we were to do ocean testing, we would definitely have a tether attached to it.
So if you're going to have a tether, is that going to affect its motion?
Yes, it would affect its motion. I mean, I don't think at this point we're doing a proof of concept. So if we were to do a pressure test, we would do that in a pressure container and pressurize that and make sure that the housing was pressurized to 1,000. I don't think we would be at the point of doing an ocean test until we had that capability. So then we could do a full, this is what it should function test. Yes.
On ethics, you discussed basically your process that you're using ethics. How about what will it be used for? Could it be used for something maybe not fully ethical?
The question was about the ethical uses of our device. Our design, our goal is to make an ocean profiler, which originally was to measure conductivity, temperature, and pressure, to develop measurements of density as you go to different depths, which is important for research with global warming and monitoring the Gulf Stream, because that's fundamentally dictated by density. There are other applications to the device. I'm sure the Navy would be interested in a device like this because it's autonomous, you just toss it off. But the same thing could be said about an AUV and other comparable devices. So we didn't consider that in the design, but it's a possibility. Yes?
Were you at all concerned with controlling the rate of descent in the device? And if so, how were you able to do that with the microcontroller?
The question was about the rate of descent, and that was brought up in the design process because we're using an open buoyancy chamber. As you dive, that air is subject to the pressure of the water, so it's going to decrease in volume and accelerate how fast the device sinks. So if we were concerned, our microcontroller has enough recycle rates to take data quickly enough to where that wouldn't be an issue. But if we were concerned about it, it would be another loop in the programming to where it's monitoring its velocity, and if it's too fast, or as it's diving, releasing air into the chamber so that it would slow its descent. The same thing on reverse happens when it's surfacing. You get enough air just to start surfacing. As it starts rising, the air is going to expand and it's going to start traveling faster up to the surface, and the reverse would be capable where you would open up that top solenoid and try to slow it down. Any other questions?
Does the company plan to patent that?
The company has shown an interest in moving forward with our project. The question was about whether the company was going to patent it, and I'm not sure about exactly if they're going to patent it or not, but they're definitely moving forward with the device. They like the proof of concept and they want to continue it and refine it and test it further.
Do you anticipate any longer-term manufacturing challenges associated with that particular design?
Yeah, I would, we didn't look into that in our research, but I would consider the manufacturing of the buoyancy chamber and the pressure housing to be the real bottlenecks on that. The buoyancy chamber was, that might came with a mold. I'm not sure how difficult that is to do. It's fiberglass in mass production. And the pressure housing was manufactured from a solid piece of aluminum. So in the future, we would most likely machine that, use extruded seamless tubing, and then weld the flanges on to the ends, and then make the kind separately. That would reduce the cost immensely and not have as much waste.
How much water needs to be displaced before you gain positive buoyancy?
The question was about how much water we needed to displace to gain positive buoyancy. And the buoyancy calculations that we came out with was, I believe it was around 500 cubic inches. No.
That's the volume of the buoyancy chamber.
Oh, that's the volume of the actual buoyancy chamber.
But we use ideal gas law to find out how much gas we need and how the pressure that we compress that to match the pressure of the water.
The device weighs approximately 40 pounds on the surface. I'm not sure offhand how much it weighs in the water, but worst case scenario, we would need around one cubic foot to guarantee that it will rise to the surface. You need much less than that. When we actually did a flow test, we removed almost all the air from the pressure chamber before it would actually sink.
Basically, when that buoyancy belt is filled with water up to about 10%, that's when it starts to become neutrally buoyant. So we really don't need that much air to release from the tank to get it to start rising. And that 10% is of about, as they said, cubic foot total space, a little more than a cubic foot.
We have the exact numbers on this side. Yes.
Looks like you guys put a lot of work into your ANSYS pressure vessel, but oftentimes hardware is a failure point. Did you look into that at all?
The question was about looking into the failure possibilities of hardware, and that is a concern in our device because we have instruments exposed to seawater. So we have the external solenoid, which is exposed to seawater, which is normally closed. So in a worst case scenario, should that fail, we'll still be able to rise to the surface. And there's also the internal solenoid. Those are the two parts that really move. And we over-engineered, the solenoid is actually rated for 3,000 PSI, which is twice what we're going to experience.
I'm sorry, I meant for the pressure vessel, the outside,
Oh, the outside.
casing. I'm sorry.
So, could you repeat?
You had the bolts on the outside, or were they? I'm not sure if they were threaded in.
Yeah.
Did you?
No,
Were you worried about those at all?
They were not threaded, and the question was about the bolts, and they're 316 stainless steel, so they're much stronger than they actually need to be. At that point, they're over-engineered to sort of eliminate the possibilities of a bolt failing. But the only stress you're getting at that is the bearing stress. So you have a shear, and because you have the entire cap there holding it in, it's a half-inch, tense half-inch 316 stainless steel bolts. It's very secure. There is corrosion issues with that because we have stainless steel touching aluminum. The hull's made out of aluminum, so there is issues with corrosion that we would have to look into further in the future. Did that answer your question?
Absolutely.
Good.
Do you have any concerns about the batteries when you get down to 1,000 feet and the cold temperatures down there, making the batteries cold so they won't put out enough?
The question was about the batteries and whether they would operate in the cold. At 1,000 meters, you're looking at around 32 degrees Fahrenheit. It's almost freezing. It's very, very cold down there. And that's within the operating range of alkaline batteries, I believe. I can't remember exactly what the operating range is for those batteries. But the power drawn from our system, because we're using the gas to do our work, there's the power draw from the microcontroller and then just to switch the solenoids, which are only open for small amounts. So that's why we only use, I believe, like 6 to 9 volt batteries, and that would give us, I believe, 6 hours of continuous operation. So that was one of the reasons why we chose a compressed gas system, so that we didn't need huge batteries and we could make the system small overall.
So 6 hours continuous operation, but how long could you leave this underwater?
For 6 hours. We can fit a lot more batteries in it. The 6 batteries was for the tests, but yeah, the 6 batteries will last you for 6 hours, and you could probably double that. You can still have plenty of space. The pressure hull is about a foot long, so there's lots of room for more power sources.
So you really did design this just for the proof of principles. You know, the production model will be bigger.
For example, we found solenoids that were smaller, that were rated for 5,000 psi, waterproof, made out of brass, but they were $1,300 a piece, and they had a 6-week lead time. And if we had those, 2 of those, we could have made the device, we could have shrunk it down half the size or even more, because that's the only reason it has a 4-inch internal diameter, is because of the heavy solenoids. So it really was, what can we get done in a small budget, and if we had more, we'd be able to make it even smaller and more effective.
Our budget throughout the project really limited our scope. Originally, our sponsor had wanted a device that was around $1,000, and he gave us a budget of $3,000. And immediately we saw that $1,000 is not going to get us down to 1,000 meters. Pressure housings by themselves, if you just order like a certified pressure housing, will cost more than that. But the $3,000 upper limit for the budget did dictate a lot of what we could and couldn't do. That's how it kind of became a proof of concept.
I really like what you did here. It's really nice. And one of the things you were talking about was just now was you could spend a lot more money and make it $3,000 valves to make it much smaller. Is there really a value added there, or could you take this and just a few tweaks to make it manufacturable, provide faculty research folks who are doing this marine research here, MMA down the road, UMass Boston up the road, with a low-cost way of gathering data? This is phenomenal. It seems to add phenomenal value to a smaller research group.
And that's exactly what our goal was in the design, was to make it as cheap as possible for research. So, I mean, that's why we didn't use the small solenoids, because cost was our major driving factor. If size was more important, then we would go to the small solenoids. But from where we are right now, we would keep it as designed. I believe, I'm not sure if that's...
That's perfect.